if you remember back to chapter 6, we looked at the energy that was associated with a chemical reaction. So if we had some reaction where a compound A was being converted to some other compound B, we said that we could report the energy change in that reaction in terms of enthalpy, okay, the heat of the reaction. And we said that enthalpy can either take on a positive or a negative value, and that the positive value meant that the reaction was taking in energy, and therefore it was endothermic, and a negative value meant it was giving off energy, meaning it was exothermic. And the way that we calculated this is to figure out the enthalpy of the reaction was to essentially take the enthalpy of the products, or the enthalpy of formation of the products, and subtract from that the enthalpy of formation of the reactants, which is all good and well if you actually have that data. Now, you may know that, or may remember that there's a table in the back of our textbook that gives us the enthalpies of formation of a wide variety of compounds. But what if we didn't have that table? Or what if we had the table, but the compound that we were interested in wasn't on there? Furthermore, let's say we didn't have time, or really the necessity to carry out a calorimetry experiment to figure out the data on our own. It turns out there's a nice way for us to estimate the enthalpy of a reaction, and that's done by using what's called bond enthalpy. Okay, and the bond enthalpy, I should say bond association enthalpy, is the amount of heat that has to be put into a system or into a bond in order to break it. So for example, we can look at a hydrogen-hydrogen bond. Okay, if we want to know how much energy that needs to be put into that bond to break it, what we need to do is basically define this as a reaction where we show the hydrogen-hydrogen bond being broken, okay, into two hydrogen radicals, two hydrogen atoms. Okay, this is what we call a homolytic cleavage, which is really just a fancy way of saying that the electrons that are in the bond between the two hydrogens, okay, are going to be divided evenly across the two hydrogens. Okay, so the energy that's required for this, okay, the enthalpy is going to be equal to 436.4 kilojoules per mole. Okay, so this tells us that in order for us to go from an intact hydrogen-hydrogen bond, okay, energy has to be put in order to get to two hydrogen radicals. Okay, so you can see here we have this change in enthalpy. Okay, that is the bond enthalpy. Okay, now we have tables that basically describe all sorts of different bonds that you can imagine. So in the table you'll see listings for things like HH bonds or CH bonds or NH bonds, and you can just simply look them up, and we can use that to figure out the energy change in a reaction. Now, the thing that we need to remember here, though, is that there are some bonds for which there's only one possible instance of it. For example, the only time you can have an HH bond is in the case of H2. Okay, there is no other compound that has an HH bond. The same thing goes for a fluorine-fluorine bond, which would be F2. okay, or say an HCl bond. Okay, hydrogen chloride would be the only example of that. But if we consider something like an, let's say a CH bond, well, there's actually several different examples of that. We could have a compound like this, methane, or we could have a compound, let's draw that out, something like benzene. Okay, which has these CH bonds. And I think that we can all look at these two compounds and agree that the nature of the CH bond is going to be different in each one of these molecules. So the value that's reported for the enthalpy of a CH bond is actually going to be kind of a weighted average of all the different types of CH bonds that have been already observed. Okay, so the table value that we would have for that would be an average value, which is where the approximation comes in, where some error can be introduced. But for the most part, these are pretty useful, and they give us a good idea of what the enthalpy of a reaction is going to be. Another source of error in this type of calculation is going to come from the fact that we're not even taking into account the states of matter. You might remember that enthalpies of reactions depended upon the states of matter of the reactants and the products. So we have to keep that in mind as well. But as long as we remember that this is, again, more of a back of the envelope kind of a rough estimation, this does the job it's supposed to do. So let's see how this works. Okay, so let's say that we want to look at the reaction of hydrogen gas with oxygen to produce water. And let's say we want to know what the enthalpy for this reaction is. Now, this is a case where you could very easily go to a database or to some table of data that would have the enthalpies of formation for all the compounds that we're interested in. But this is just a model, just to show us how it's done. Okay, so when we look at these compounds that are involved in the reaction, the first thing we need to do is we need to balance things, which means a 2 goes in front of the H2 and a 2 goes in front of the water. Now we're going to draw Lewis structures for every compound that's involved. Okay, so we have 2 molecules of H2, and we have 1 molecule of O2. Okay, you can see here why it's important for you to be able to draw a Lewis structure fairly quickly, so you don't have to kind of languish over this part of the process. Okay, so we're going to take those and we're going to form 2 water molecules. I shall be consistent here with my dots. So you have the first water molecule and a second. Now, if we take an inventory here, okay, we can look at the number of hydrogen-hydrogen bonds we have on the left side of the arrow. And we can see here that we have a hydrogen-hydrogen bond here and a hydrogen-hydrogen bond here. And if we look over on the product side, we notice that there are no hydrogen-hydrogen bonds anymore, which means, okay, we are going to break 2 hydrogen-hydrogen bonds. Okay, we also see that we have oxygen with its oxygen-oxygen double bond. And we notice that in the products, there are no oxygen-oxygen double bonds. So we're going to be breaking 1 OO double bond. Now focusing on the products, we see that we're going to be forming some bonds. Okay, we have HO bonds here that were not present in the reactants. Okay, so for one molecule of water, we have two OH bonds. Okay, but we have two molecules of water. Okay, so that means that we have a total of 4 OH bonds. Okay, that are being formed. Okay, so to calculate the enthalpy of the reaction, okay, what we need to do is we need to look at the amount of energy that's being put into the reaction by breaking bonds and how much energy is being released in the reaction by forming bonds. Okay, now in the past we've always seen that the change in a reaction is measured by looking at the final minus the initial, the product minus the reactant. But because of the way that bond association or bond enthalpies work, the signs are kind of funny. So instead of taking the products minus the reactants, we actually take the reactants minus the products. So the enthalpy of the reaction is going to be equal to the sum of all the bond energies of the reactants minus the sum of all the bond energies of the products. Okay, and again, the main reason for this has to do with the sign of the answer, whether it's positive or negative. Remember, if we're putting energy in, okay, the bond enthalpy is going to be positive. Or I should say, the contribution from the bonds forming is going to be a positive value. And for breaking is going to be, actually I said that backwards, and that's not really that important anyway, so let's just leave that at that. So it's going to be the bond energies of the reactants minus the bond energies of the products. So we need the bond energies for each of these types of bonds. Okay, we've said that the HH bond is 436.4, and that's kilojoules per mole. Okay, the oxygen bond is 498.7 kilojoules per mole. And the OH bond is 460 kilojoules per mole. Okay, it's interesting to take a look at these numbers here, because you'll see that the numbers for the HH bond and the OO bond have 4 significant figures, whereas the one for the OH bond is going to have only 2. And the reason why we see less precision in the value for the OH bond is because there's a lot of different molecules that can have an OH bond in it. So that's going to be an average of many different molecules. Whereas there's only one compound that has an HH bond and there's only one compound that has an OO double bond. So those numbers are specific for those particular compounds. Okay, so the enthalpy of this reaction is going to be equal to the sum of the bond energies of the reactants. So the reactants being the hydrogen and the oxygen. So for the hydrogen, we have 2 times the bond enthalpy for an HH bond, which is 436.4. And for the sake of keeping things kind of tidy here, I'm going to leave the units out. We just have to remember that we need to put the units back in at the very end if we take them out now. And we have 1 OO double bond, so that's 1 times 498.7. And we're going to subtract from that the bond energies of the products, or enthalpies of the products. which is going to be 4 times 460. Okay, now all we have to do is run out this calculation. And what we wind up with here is negative 468.5 kilojoules per mole, telling us that the reaction is exothermic. Now, can we say for certain that we're dealing with exactly 468.5 kilojoules being released for every mole? Probably not, but it would be pretty darn close. Okay, so and that's how we carry out these calculations. And the number for this answer is actually, it makes a lot of sense if you've ever done this reaction before. If you take hydrogen and oxygen and you spark them with a flame, you do make water, but you also make fire. So this is definitely an exothermic process, so it's nice to see that the calculation matches up with the experimental observations.